Assalamualaikum and very good morning. We are pleased to present our group project entitled Passive Cooling System Design and Optimization. This project focuses on the design and analysis of a passive cooling system with the aim of improving heat dissipation performance through optimized heat sink design. We present this project to Prof. Madia Dr. Azwan bin Sapet. Next. Next, moving on to the introduction. As we know, thermal energy moves due to temperature differences via convection, and radiation. In electronic systems, efficient heat transfer is critical to prevent overheating and ensure safe, reliable operation. To address this, our project focuses on passive cooling using heat sinks or fins. By geometrically increasing the surface area, these fins significantly boost heat dissipation through natural convection, completely eliminating the need for external power. To identify the most efficient configuration, our study takes a two-step approach, which is first, establishing baseline expectations using theoretical calculations, and second, simulating and analyzing different fin designs using SolidWorks flow simulation. Now, let's take a closer look at our specific project objective and the methodology we use to achieve this. Next, I will present the objective of our project. The first objective is to analyze the thermal performance of a passive cooling heat sink system by applying basic heat transfer principles such as conduction through the heat sink and natural convection to the surrounding air. The second objective is to develop and validate a 3D model of the passive cooling system using SolidWorks flow simulation where the heat transfer behavior and temperature distribution are simulated and compared with the theoretical results. And the last one is to optimize the heat sink design through a parametric study by varying key parameters such as fin number, thickness, and height in order to improve the overall cooling performance. Next, let's continue to our literature part. For the literature review, previous studies show that the performance of passive cooling system mainly depends on the heatsink design, especially the fin geometry and arrangement. Heat is transferred from the chip to the heatsink through the conduction and then released to the surrounding air by natural convection. Aluminum alloy 6061 is commonly used because it has a good thermal conductivity, is lightweight, and has a good corrosion resistance. Rectangular straight fins are widely applied due to their simple structure and effective heat dissipation. However, fin dimensions, number, and spacing significantly affect the cooling performance, so proper optimization is required. In this study, thermal resistance analysis and SolidWorks flow simulation are used to evaluate and improve the heat sink performance. Next, let's continue the next part. For the specification of this passive cooling system, the heat source applied is 10 watt with an ambient temperature of 30 degrees Celsius. The maximum allowable chip temperature is set at 85 degrees Celsius. The heat sink material used is aluminum alloy 6061 due to its a good thermal conductivity. The maximum base size is 60 mm by 60 mm with a maximum height of 50 mm. The cooling mechanism used in this design is natural convection without any external fan. Next, let's continue to our methodology parts. Thank you.
Hello and Assalamualaikum. My name is Muhammad Fakhrul Aiman bin Muhammad Fazil and my numbermetry is CD230229. I'm going to presenting about phase 1 which is base case calculation. And the table show that this is our specification and on the right side is our sketch diagram. Okay, we go to the next slide, which is the calculation. First, we need to find the fin efficiency. And next, we need to find the effective area. And then the convection of resistance. After that, we need to find the conduction resistance of the base. And lastly, we need to find the chip temperature.
Moving on to phase 2, which is the simulation part. For the model setup, a 3D heatsink model was developed in SolidWorks and analyzed using external flow simulation. Air was selected as the working fluid, while gravity was enabled to simulate the natural convection effect. The heatsink material was assigned as aluminum alloy 6061 and a heat source was applied at the chip location to represent the actual operating condition of an electronic component. As we can see, the figure besides, the top section represents the heat sink fins, which is the material used is aluminum alloy 6061, while the chip is located underneath the base, which is the material used is silicon. Next, let's continue to our next part. Thank you. Next, for the simulation results, the first figure shows the surface temperature distribution of the heatsink model of an isometric view. From this figure, we can observe the temperature variation across the heatsink structure. The highest temperature occurs at the base where the heat source is applied, and the heat gradually spreads to the fins, causing the temperature to decrease towards the fin tips. This shows that heat is effectively transferred and distributed through the heat sink before being released to the surrounding air. As we can see, the second figure shows the flow trajectories for velocity around the heat sink. The airflow pattern can be observed moving upward through the gaps between the fins. This occurs because the heated air becomes less dense and rises due to buoyancy effects. The airflow movement indicates the natural convection is taking place and helps remove heat from the heatsink without using an external fan. Next, we will continue for our phase 3.
In phase 3, we move into design optimization using a higher heat load of 15 watts to test the limits of our system. For iteration 1, we modified the base design to feature 7 rectangular fins with an increased thickness of 3 mm. As you can see in the temperature surface plot, the heat is distributed across the fins, but the reduced fin count provides less surface area for dissipation compared to our original base case. Looking at the flow trajectories and simulation graph, the solution stabilized at approximately 79.47 Celsius after 40 iterations. While this is safely below our 85 Celsius limit, the temperature rise compared to our 10 watt base case indicates that reducing the fin count to 7, even with thicker fins that provides less effective cooling due to the overall reduction in surface area available for natural convection. Next, for iteration 2, we explore a geometric change by using 9 rectangular fillet fins. By adding a fillet to the fin profile, we aim to improve the airflow transition at the base. This design maintains the 3 mm thickness and was tested under the same 15-watt heat source. The surface plot shows a more uniform temperature distribution compared to the previous iteration. Next, the results for iteration 2 were very promising, stabilizing at 77.35 Celsius. Interestingly, this design performed better than both the 7 fin and 10 fin variations we tested later. This proves that the filleted geometry successfully reduced local flow separation at the fin base, enhancing convective heat transfer even with a lower fin count than the original base case. Next, in iteration 3, we return to the original count of 10 rectangular fins but keep the optimized 3 mm thickness. Theoretically, returning to more fins should improve cooling. However, the surface plot shows that the heat remains concentrated at the base, similar to what we observed in iteration 1. The simulation graph shows that the iteration 3 stabilized at 79.47 Celsius, exactly the same result as the 7th fin design. This was a critical finding for us, as it suggests that simply matching the fin count of the base case with thicker fins under higher heat loads does not necessarily yield additional cooling benefits. It highlights that the relationship between fin count and temperature is non-monotonic in natural convection. Finally, we push the design to its limit in iteration 4 by increasing the count to 12 rectangular fins. While this provides the maximum total surface area among all iterations, the narrow spacing between the fins becomes a significant design concern for buoyancy-driven airflow. As shown in the flow trajectories and graph simulation, iteration 4 produced the highest maximum temperature at 84.79 Celsius, which is just under our 85 Celsius safety limit. This design failed to improve cooling because the closely packed fins cooked the natural convection. The restricted air channels trap warm air between the fins instead of allowing it to rise freely, demonstrating that for passive cooling, balancing fin spacing is more important than merely maximizing surface area.
Hello, my name is Shafiq Aiman and my metric number is CD230186. So first let's us look at our result. We analyze that the chip operating temperature, so we ensure it stay below the safety limit of 85 Celsius under standard 30 Celsius ambient condition. So then we move on to the model validation. So to start the validation, we use the manual hand calculation, and the predicted result was the 62.65 Celsius, while our SolidWorks simulation showed 74.34 Celsius. So both method gave us a pass safety status, meaning that our baseline design is safe. So we move on onto the parametric design studies. So we test different fin design to see how they affect the cooling. So our best case scenario that with the 10 fin was the most effective because it kept the chip temperature at 74.34 Celsius, and then we test the by lowering the fin count to 9 or 7, and this caused the temperature to rise. But surprisingly, when we add more fin, 12 in total, caused the temperature to jump up to 84.79 Celsius, which is the right on the edge of our safety limit. So let's see the validation disparity. So as you can see, this is the differences. So there is 19.81 relative error between our hand calculation and the simulation. So this is because the hand calculation use simplified 1D assumption, where the simulation capture realistic 3D airflow and heat path. So the simulation give us a safer and more realistic boundary. So as for the 10th, uh, 10th our 10th fin design, it gives us a comfortable of 10.66 Celsius safety margin. It provides the perfect balance, enough surface area to let the heat escape, but uh, but enough space between the fins for cool ambient air to flow smoothly through the channels. Lastly is the thermal choking. When we did the 12 fin, it performs so poorly. So this is caused by the phenomena called thermal cooking. Even though the 12 fin give us more surface area, but the gaps between them become too narrow. So this trap the hot air and choke the natural airflow, which causes the temperature to rise up to 84.79 Celsius. So ultimately, this proof that when it comes to fin density, more is not always better.
Next, for the conclusion, the project successfully validated the aluminum alloy 6061 heatsink with SolidWorks simulation providing a realistic 74.34 Celsius compared to the 62.05 Celsius manual estimate. All iterations remain safely below the active 5 Celsius limit, confirming the system reliability for passive thermal management. A key finding was that increasing fin density can counterintuitively choke natural convection, as seen when the 12-fin configuration raised temperature by restricting airflow. Ultimately, effective cooling depends on a strategic balance of fin count, spacing, and geometry rather than the simply maximizing surface area. So that's all from us. Thank you.